Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.38. This is a pretty creative problem. In the movie The Drowning Pool, private detective Lou Harper, played by Paul Newman, is trapped by the bad guy in a room containing a swimming pool. The room may be considered rectangular, 5 meters wide by 15 meters long, with an open skylight window 10 meters above the floor. There's a single entry to the room, reached by a stairway, a locked 2-meter high by 1 meter wide door, whose bottom is 1 meter above the floor. Harper knows that his enemy will return in 8 hours and decides he can escape by filling the room with water and floating up to the skylight. He plugs the drain with his clothes, turns on the water valves, and prepares to put his plan into action. Part A. Prove that if the door is completely underwater and h is the distance from the top of the door to the surface of the water, then the net force exerted on the door satisfies the inequality. The force on the door is greater than the density of water times gravity times the height times the area of the door. Don't forget that a pressure is also exerted on the door by the outside air. So right here we've got our room. We've got our room here. We've kind of modeled that as 5 meters by 15 meters. We've got the total height. The skylight is 10 meters up. I've got like a little staircase right here. Well, that staircase leads to a door right here that is 1 meter wide and 2 meters tall, and it's 1 meter off the floor. Okay, we know that the bad guy's coming back in 8 hours. Alright, so here's a force balance of what's going on with the door. We've got a pressure on the inside with the water kind of pushing, and this is an average pressure. And then we've got an average pressure pushing on the other side, which is just atmospheric pressure. Okay, so let's make our reference plane for our reference plane is the top of the water, and h is the distance from the top of the water to the top of the door, like they said. Okay, and z is the distance from the top of the water to wherever we want to be. Okay, so the pressure on the door at any point on the door, as I travel down z, the pressure at any point on the door is going to be bigger or smaller depending on where I'm at the door. So the pressure at the top of the door is going to be a little smaller than the pressure at the bottom of the door. That makes sense because the door is kind of long, and that's an extra 2 meters of water that is going to be pushing on the door, right? So this is our function for the pressure on the inside, but it's a function of z. So depending on where we are in the z direction, we're going to be having more or less pressure. Okay, so that's what this is. That means pressure on the inside is a function of z. Well, what is the average pressure? Well, the average pressure, if we take the sum of all the pressure over the full length of the door from Z0, which is at the top of the door, to Z1, which is the bottom of the door, if we sum up all of the pressures along that door in the Z-axis, then we'll have the total pressure along the Z-axis, but then we need to divide that by the Z-axis so that we're still in units of pressure, because if we multiplied it by 1 Z, then we have to average it over the entire door, and so this will give us the dividing by z, the total length of the door, will give us the average pressure across the whole door. So we sum up all the pressures along the door, and then we divide by the length of the door. if that makes sense. You can kind of conceptualize. We're taking each little pressure along at each point along the door, we add them all up, so it's kind of like taking an average where you have a sample and you add up all the samples, and then you divide by the number of samples. Well, we're dividing by the length of the door, so after we average up all the little pressures along here, then we divide by the length of the door. It's kind of like dividing by the number of samples. All right, so that's how you take an average with an integral. Okay, now we've got our average pressure. We just perform the integral here, and then we evaluate the integral at z1 and z0. And then this is just a bunch of algebra canceling out terms. We substitute in h because our function that they want us to compare it to is a function of h, so we'll substitute in what h is instead of z. You'll see that h is the top of the water to the top of the door, so that's h, so z0 is equal to h, and z1 is equal to h plus the length of the door, so h plus z door. So we substitute in those here and there. I ran out of room here, so it's a little confusing, but you can see on the next line how that works out. So it ends up, you know, our reference pressure, all those little z's and z doors end up canceling out, and h's cancel out. But here we actually have a couple of terms left over. So we expand our squared terms here, and some of the h's cancel out and some of the z doors cancel out, but we're still left with an extra term here, and it ends up canceling out to the point where we have our reference pressure, we have the term that they were talking about, which is the density of the water times gravity times h. But then we also have a little bit extra right here. We have our density times gravity times the length of the door divided by 2. So that's because we're averaging over the full door, there's a little bit more pressure there, okay? So, and then we'll say that the average pressure on the other side of the door is P naught. So that's our reference pressure, our atmospheric pressure. Okay. So then we have, okay, so the net force from our force balance that we did earlier up here, our force balance, we say our net force is the area of the door times the difference between the pressure on the inside minus the pressure on the outside. Okay, so that cancels out our reference pressure, our P naught term, and we're just left with rho GH plus this extra term. So you can definitely see that satisfies part A, where it's saying the force is greater than the area of the door times just rho GH. It also has this extra term here because it's over the full door, so we're averaging over the full door. It's not just at a single point on the door. So let's do part B. Assume that water enters the room at about 5 times the rate at which it enters an average bathtub, and that the door can withstand a maximum force of 4,500 newtons, about 1,000 pounds force. Estimate 1, whether the door will break before the room fills, and 2, whether Harper has time to escape if the door holds. State any assumptions you make. Well, okay, so the average volumetric flow rate of a bathtub is about 5.5 gallons per minute. So if we convert that into 5 times that volumetric flow rate and we turn it into meters cubed per second, we get this. Okay. Then the total amount of time, remember, was delta t. It's 8 hours. We convert that into seconds, just so we have everything in standard units, SI units. So we're working in seconds here. We've got 2.88 times 10 to the 4 seconds. Okay. Well, now let's look down here. So we've got our net force here, and now we're going to assume that the water goes all the way up to the skylight, okay? Because that's the region where our equation is valid. In this equation, remember, we assumed that the water level was above the door. So this function only works for when the water level is above the door. Okay, so we're going to assume that we made it all the way up to the top of all the way up to the top, to the skylight, so that's 10 meters up, and h is measured from the top of the water, which is 10, minus the top of the door. The top of the door is 3 meters up. Okay, so that's when h equals 7. Okay, so the net force when h equals 7 is equal to this, and that is 157,000 newtons. That's way above what the door could handle, which is about 4,000 newtons. So no, the answer is no, the door will not hold that pressure. The door would fail. Okay. The second part asks us whether Harper has time to escape if the door holds. Well, I said, okay, well, how long would it take? I said, we don't know exactly at what point the door would fail. And I thought, hey, what if he just made the door fail instead of going all the way up to the skylight? Why doesn't he just like go out the door if he can bust down the door with the water? So I thought, how long would it take for the water to get to the top of the door so that our force equation would be valid? So I said, okay, if L is the liquid level, how long until L is greater than 3? So this is our L equation. L equals the volumetric flow rate times the amount of time that has elapsed divided by the cross-sectional area of the room. And remember, it's a pretty big room. It's 5 meters by 15 meters. Okay, so we've got our, we're solving for, okay, at what time does L equal 3? Okay, so then we solve for T here, and we solve that in order for the water to get all the way to the top of the door, 1.3 times 10 to the 5 seconds would have to pass. And as you can see, that is well above 8 hours. So it would take longer than 8 hours for the water to get to the top of the door. Well, then I thought, okay, well, we can't use our force equation because the water would take so long to get up to the top of the door. Well, maybe we could write a different force equation for the region where the water is not necessarily higher than the door, but it's somewhere halfway up the door, and maybe there's still enough water pressure to push the door through, right? So maybe we can look at, okay, how long does it take for the water to get to the bottom of the door? Okay, so that's what this one is. How long does it take for the water to get to the bottom of the door, which is 1 meter up? Well, that would take 4.32 times 10 to the 4 seconds. And that is still, unfortunately, larger than 8 hours. Okay, so T1 is greater than T2, and both of those are greater than the amount of time that it would take to for 8 hours to elapse. Okay, so there is no chance that this escape plan will work. He will not even have gotten the water level up to the door. And again, that's assuming that you have 5 times an average bathtub flow rate, which is about 5.5 gallons per minute. All right. Well, if he had more water flow rate, he might have been able to do it. Maybe if he had 10 faucets. Anyway, well, that is it for problem number 3.38. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.